So exercise number 1 involves a city water treatment facility. The current line has a normal flow rate of 1,350 cubic feet per minute with a standard deviation of 600 cubic feet per minute. The maximum the line can take is 2,750 cubic feet per minute. We want to know the probability that the flow rate will exceed the sewer line capacity and cause a backup of sewage. So we're going to assume this is normally distributed. Of course, that's easy to test. We're going to go into BlueSky. We're going to go to the distribution function. We're going to choose normal. We want a normal probability. And the numbers were, excuse me, we want to know a probability associated with the upper limit of the capacity of the sewer line, 2,750. We have a mean of 1,350 and a standard deviation of 600. And with BlueSky, we're going to try to find the upper tail of that distribution. We execute, and BlueSky's answer is 0.98%. It's also helpful to plot this graphically. So if you go to the normal distribution menu, click it, you go to normal distribution plot, click it, enter your mean and standard deviation, and what you want is the density function. And let's look at the numbers above 2,750. What's that look like graphically? If you click the execute dialog, BlueSky will give you this plot. And that's what we need to include in our reports to illustrate this idea. So it shows the percentage above 2,750. We already know that's roughly 1%, but the graphics make it easier to see. Problem number 2 involves an insurance agent who wants to see what the probability is that there would be no accidents in a 30-day period in a given intersection. On average, that intersection experiences 2.27 accidents per month, and we're told it's an exponential distribution. So let's look at how BlueSky would solve this. First of all, BlueSky can calculate exponential probabilities. You pick distribution, you drop down exponential, and you pick exponential probabilities. We've done that for our problem. We want to know the probability of one or more accidents at the intersection when we have an average of 2.27 per month. And when you run this calculation, when you execute this dialog, you get this number from BlueSky, so 0.8967, roughly 90%. To get a graphical view of this, you simply go to exponential distribution plot, enter the rate, 2.27, and click execute, and BlueSky will produce this chart for you. And that shows the same thing, 90% below 1. Now, I'm going to let you in on a little secret. The exponential distribution is normally used when you're interested in probabilities on a continuous scale, but it's very closely related to the Poisson distribution. So if you go to BlueSky and you choose Poisson distribution, you look at the probabilities of a Poisson, you can enter these numbers, and you want to know the probability of 0 for a process that has a mean of 2.27, the upper tail. You calculate the Poisson probability, and it's identical to the exponential probability. Likewise, you can plot the distribution plot for a Poisson. And what it does is it gives you discrete probabilities. So the probability of 0 is 1 minus that. The probability of 1, 2, 3, etc. accidents per month are shown on this plot. So I personally find this more useful, and it's an option for you as well. For exercise 3, we're given a pharmaceutical company's developed an IV drip device that has a target drip rate of 5 drops per minute. We take a sample of drippers from the lot and we test them by counting the number of drops that fall in a 10-minute interval and divide by 10 to get drips per minute. Here are our results. It tells us to use a two-tailed t-test to test the hypothesis that the process mean is equal to the target 5 at a 5% significant level. So what we did is we typed these sample values into a spreadsheet and we saved it. Now we want to analyze that data using BlueSky statistics. So we're going to open the data set. And the file name is IV drips. We open that data set and BlueSky brings it into the program. And there's our information and there's our sample values. Now we're going to go into the analysis tab and we're looking for a test of a mean, and we want a one sample t-test. So we're going to click that option. We want to analyze drips, and we're going to test the hypothesis that the population mean is equal to 5. And we're going to test it at a 95% confidence level. We execute the dialog. BlueSky does its thing. And what BlueSky tells us is that, first of all, some summary statistics. Sample size, mean, standard deviation, standard error of the mean. Our test value is 5, and the results are not statistically significant. So this means that it's less than 0.05. That means that the drip value is not equal to 5. It's not in the confidence level. So this tells us that the average difference is minus 0.02111. The lower confidence interval is minus 0.4. The upper confidence interval is minus 0.0211. And the zero difference value is not in that interval. So we conclude that the drip values are not equal to 5 on average. For exercise 4, we're told that the above pharmaceutical company historically had a process variance for IV drips of 0.028. And we want to know what the critical value of chi-square is for getting the sample result if the process variance is still 0.028. In other words, if the process variance is 0.028, what is the probability of the sample variance actually occurring? So we can solve that problem by, first of all, calculating our sample variance. And when we do the calculation, we can do it in BlueSky or Excel. So the variance of our sample is 0.06111. The historical variance is 0.028, and we took a sample size of 9. And this is the calculated value of chi-square. So it's equal to the degrees of freedom times the sample variance divided by this denominator. So what we're asking is, what are the odds of getting this variance if that's the true historical variance? And the variance is a highly variable estimate, so it could possibly be, we need to test it with statistics. So we're going to use BlueSky's chi-square probability, and that's where it's at on the menu. To see what the chances are of getting this value of chi-square from 8 degrees of freedom, we're interested in the upper tail because that's where we'll reject the hypothesis. We click execute, and BlueSky tells us the chi-square probability is 0.02566. So that's less than 0.05, meaning that we reject the hypothesis. So our problem seems to be that the process variance has actually increased. For exercise 5, we're told the variance of machine X based on a sample of 25 is 100. Machine Y's variance based on a sample of 10 is 50. The manufacturing representative from the supplier of machine X contends that the result is a statistical fluke. Assuming that a statistical fluke is something that has less than 1 chance in 100 of occurring, we're going to test the hypothesis that both variances are actually equal. Now notice that machine X has a variance of twice what the variance is of machine Y. So we want to test the hypothesis that the variance from this sample, even though it's double, is not statistically meaningful. So if you go into BlueSky, you choose the F distribution, and we want the F probabilities. We want F probability for a difference of 2 times, with 24 degrees of freedom in the numerator and 9 degrees of freedom in the denominator. So we will click the dialog execution icon, and BlueSky will give us that F probability, and it's 0.14. So there's a 14% chance that these two variances are equal, in spite of the fact that one is double what the other one was, because the variances are a very highly variable statistic. So in other words, the manufacturer's representative was correct.